Okay, so I'd like to apologize for the technical errors and not getting through all of the lesson for the first class. For those of you who had technical difficulties, please make a time to meet with me. I would love to, work through it with you and figure out what's going wrong so that we can, you can get something useful out of this class. I'll be discussing with Dr. Arantes the things that happened, the technical difficulties. I know my computer froze. I had to shut it down and restart in the second session. I know some of you had technical difficulties with R. Um, we're going to discuss that and come up with a plan for the homework, be it more time um, or maybe altering or removing some of the questions or maybe making them extra credit. I'm not sure yet. We'll decide and then I'll send out an email to the class about it. But I do want you guys to get a lot out of this class if you're interested in it. And I don't want you to struggle and stress too much about it. So just look for an email from me about that in the future. So I'm going to go through and make a clean video where I can go slow and hopefully uh, make everything a little more clear for you so that the homework's not too challenging. I don't want this to be a stressful event for you guys. I want you to learn R and understand it and be able to add it to your toolbox going forward. So I'm just going to start here on the lab page. You should have watched this introduction video. I'll be adding this lecture video, and I think I'll make another lecture video using Mac. Um, and hopefully that'll help some of you. Here's that guide I referred to. This is the folder you need to download. This PowerPoint has just some information about R, and it should like be kind of a pictured guided tutorial of just like the environment more or less. Here's the worksheet for the homework, and this is installing R on Mac. So if you have Mac and you had trouble doing that, please check that out. So I'm just going to download this folder, which I already have downloaded, but it pops up here. You download it and it's zipped. So I have it right here. I'm going to go extract all. I'm going to delete that and extract, and we'll see. Hopefully that'll work. Yeah. So it's Lab 6 Intro to R. Again, that guide is in here in a PDF and an HTML format. I like the HTML format. If you had trouble following these links, let me know. I guess I can make a video. I know I made one for Mac. I can make a specific one for Windows, but again, it's just click that, download and install following the whatever installation wizard it is, and then the RStudio install page. I think I went through this all. It's just this is all I did: install RStudio for Windows. And again, that was pretty much the same. So we're gonna just go through. This is the folder. I like to have it fairly organized. In that first video, I went through my first R script. I have a data folder. I like to keep my raw data here, and then I like to save my clean data here in a clean data folder and keep them separate so that if I messed up or whatever, I can just go back and reload and do it again. I tend to keep a data log where I put the date and then just some notes indented about the data, not necessary for this class, but if you're ever, using a really large, you have a really large project, say you go to grad school and you're doing a thesis, Especially if like, you know, you have a field season and you're doing analysis and then you do the field season and it's like a month before you get back into it, it helps to just remember where you were. So you'll see right now, there's no RStudio project in here. There's just the scripts. These icons may not show up on your computer because it may not be set to default to let RStudio open those, but anything that's .r is an R script. This figures folder is where I like to save my figures just to keep it organized. You can save it to this folder, which will be our main directory or our working directory. It's your preference. So I'm just going to minimize that and then open RStudio. RStudio opens. This is a blank session. I want to go back to Cobalt. I think I showed you guys this in the first video, but I do really prefer Cobalt. So I'm going to go to File, New Project, and in Existing Directory. And it doesn't matter where you put that folder as long as you can find it. So I know I put mine on my desktop. You might have a folder for your class. So I'm going to do Lab 6 Intro to R Project Students. I'm going to open that. I'm going to hit Create Project. It's going to load. And you can see here, this is my new working directory. And I have my R scripts, my data folder, my figures. This is the R project link. My first script, which we went through in the previous video, and then those two guides. So if I close out R, the nice thing about that is you can click that icon and it'll open this R project, the session, the working directory is all the same. This is my R version. That's the newest one, I believe. If you have an older R version, I guess I'll put a video about updating R if I can. It shouldn't be too tricky. If you have RStudio, you can like check for update for packages. Somewhere in here, check for updates for RStudio. I don't think I have the newest version of RStudio. I can't update RStudio because I don't have permission to do it. This is a school computer. But it hasn't changed too much in my experience between various versions. And I think this is fairly new. So hopefully that is the same for you guys. And if it's not, let me know and we'll work through it. So we're going to, I'll do this. I'm going to open this just because. So some of you said you had trouble installing packages, and this shouldn't be too difficult. You go here, sorry, to packages. So it's in mine. I have files, plots, packages, help, and viewer here. And again, that is if you go to global tools, global options, and then pane layout, you can set this to match mine. Console is here. That's this. This is where my code is executed. Source. So this is where my scripts are. Environment history and all that. It doesn't matter. I hardly ever use that. And then over here, I like to have my files, plots, packages, help, and viewer on the right. So that's how I have mine set up. Yours might be different. It doesn't matter. You'll just have to figure it out. I think this and this are switched more or less. I think that's really the only difference besides the theme for mine, but you'd hit apply and then okay. So to install, you just simply do this, install TIDYR, click that and install, and it should run through and install. Mine are already installed, so it's not gonna like take as long. And I'll try to put timestamps for this video, so you don't have to waste too much time watching all of this. So that's the Dippler package. If I wanted to do it via code, I could do install packages. And if you're doing it in RStudio, it pops up. I'm not sure. I think you don't want installed packages. You want install packages. So you can actually just click this, and then it has to be in quotations, FSA, and hit enter, and it will run. And then I'm going to go back here and do it. I like to do it this way because it's nice. And install. And when you're doing that, like having this install dependencies is useful. But my hope was that you had all this done before class. And maybe you guys all did, and there was just some other error that came up. It's hard when I can't see, when I'm not there with you. It's hard to troubleshoot, unfortunately. That's just what we have to deal with here during COVID. So after you install those packages, you have to load them, and you do that with this library command. So every function we use in R, you write the function in name, in this case library, and then you have parentheses, and then within that parentheses you put the command for executing that function. In this case, we're putting the package name, and it doesn't need to be in quotations this time. It can just be the name, but you have to check the spelling. But it should all be correct because I provided this code for you. So we're just going to run that. And the way I like to run it is I just put the cursor on the line, hold control and hit enter, hold control, hit enter. The other way, you can go up here to run and hit run. I think if I did this, yeah, I don't know. I guess that's not super useful. There used to be a way to run all code above a certain point. Maybe they took that out. So you can ignore these mostly if you're getting these particular commands saying attaching this package, the following objects are masked, hidden from the package stats, and it's filter and lag. Yeah, these are masked from the package base. This is just saying, hey, please cite this if you run it and then use your analyses to publish. This is loading some dependencies, so the permute in the lattice package, and then it's telling me the version of vegan. So you can safely ignore all of that. If you have an error that says FSA was built under version whatever, that means you have an older version of R. For the most part, that doesn't matter. It didn't matter when I was creating this with my older version of R. If it does, you'll have to update it or load an older version of that package, which is more difficult. But those are things we can troubleshoot together. So this directory command, it is a way to just show what's in a folder. So if I just type in directory, it shows me what's in my main working directory, which is that folder I showed you right here. But here, if I type a path in, which has to be in quotations, so I want to look inside the data folder, and then within that, you have to use this to separate folders and items. I want to look inside the raw data folder, so I can see I have this CSV file here. Now, the reason I'm using a CSV file is it's the most simple way to upload data into R. So if you have an Excel file that's just regular Excel, so I think that is generally XLSX. You would do save as and come down. There's other CSVs. I've never used those. And the one I was taught to use is this one, CSV, comma delimited, and as a star CSV. And then you just hit save. So we're going to read our data in now. And so R is an object-oriented data system, which means we're creating objects. In this case, our object is Ohio. I could name this anything I want, DAT or whatever, but I named it Ohio, and I suggest you keep that because you'd have to change it everywhere I use that object. This is your assignment operator. So anything that you do on the right, whatever function, is going to be assigned to the object on the left, in this case, Ohio. So this function, read.csv, will read in a CSV, which I just showed you. The first command here is the path or the file itself. If the file is just in your working directory, this is all you need. But because I have data, raw data, and then my CSV, you have to type in that path. And that needs to be in quotations. So you need to separate your commands within a function by a comma. And then the next command here I'm using is NA strings. So this is saying what should be read in as an NA, and then use the equal and then C. So it's going to read in this as a vector. A vector is a string of either characters, numbers, or logical values. In this case, they are characters. You can see that because they are in quotation marks. So here, and by default, R will read capital N, capital A as NA. But if you have a blank cell in your spreadsheet, you'll have to put in just quotations with no space or anything there. If there was a space in that cell, you may have to put a space in there. What else? I've also seen people do this for missing values. If you want that to be an NA, you'd have to add that. But that's not necessary. That's not here or there. That's not part of our data. So this is all you should need. I know some of you had trouble making this path work, and I'm not sure why that was, but you'll have to come and meet with me so we can troubleshoot. I'll really have to have you share your screen and look at it in order to do that. So we're just gonna run this code, put my cursor there and control enter. And of course I could have this all on one line. It just isn't as easy for me to read it, and it would work just fine. But I like to have it on 2 lines, and it does this nice indentation so I can see. And if I ever got confused by my parentheses, if I just put my cursor there, it highlights that. If I put it here, it highlights that. So it tells you which parentheses are closed. And say I did this, all of a sudden I get errors, right? So it's saying, uh-oh, there's an error on this line. This parenthesis not closed. And then I get one on this line. It's saying, hey, this is that parenthesis. And then it's also, because it's searching in every other line for a parenthesis that's going to finish that code. But this opens it, this opens it, this closes it, this closes it. So it's not there. So it's going to give me errors everywhere. So you'd have to add that parenthesis in, then click, and it goes away. So I have loaded my data, and it's there. So this head command just shows the first 6 rows of data. It's just a nice way to look at it. You can see these are the row numbers. So when it breaks like that, you can keep track of it. These are your column names or variables. Each row generally corresponds to an observation. So if you see when I run this structure command, abbreviated str, it's going to say that this is a data frame. And that's going to say you have this many observations or rows, and then 20 variables or columns. And then you can see the name here, and you can see the way that that is encoded. So these are characters. This is an integer, so it's a whole number. This is numeric, so it has a decimal place. There's also logical values, which would be like true or false. And then we're going to create some factor values. And currently date is a character value, whereas we want it to be a date value. So I listed out the variables we want to change and what they should be. Most of them are going to be factors. E time, so electrofishing time, is going to be numeric, and then date is going to be a date format. So I'm going to show you this way to do it. You could do this, and I will show you later how to do this up here, all in one step. But basically what we're doing here is we're taking the Ohio data frame, and we're overwriting the Ohio data frame with everything that we're going to do on the right of this piping command. So this comes from the Dipler package. So does this function. And the Dipler package just provides kind of a nice, easier, cleaner way to code. So it's easier to read. So what this is saying is pass this right to anything like whatever function, in this case, mutate over here. I could do it separately. I could do mutate, and then you'd have to put in the data frame and then event code like that. But using piping, you don't have to do that because it just knows because you're sending it on. And it's a lot cleaner. And you can, as you'll see later, you can string multiple commands together. Oops. And I could do sort or arrange, you know, but we're not going to do that now. So what this is saying take the event code variable, and it's just saying equal. So apply what's on the right to the left. And we want to use this factor function. So we want to convert whatever is inside here, which is event code, to a factor. So it's just going to rename this as a factor or reclassify as a factor. And we're going to do that for all of these variables. E time, we want to be a numeric variable. So we're going to use as dot numeric. And then again, it's just E time in here. Pay attention, we are separating all of these commands by commas. And then date is a little more complicated, but not too much. Date equal as date, and it's capital date. Then you have to put in the variable here, date, comma, and then you have to tell it the format. So the format equals, and that's going to be a character string. So if I look over here and I do Ohio $date, and it pops up right here. It's a real nice feature of RStudio. And enter that, you can see the format of the date variable, and that's the format you need to enter here in format. So it's a 4-digit year separated by a dash, not a slash, and then a 2-digit month, and then a 2-digit day. And if you needed to look that up, you go to as date. So I'm going to go to help, not packages, and type in as date, and it should pop up here. You might have to type in a little more depending on which function. And it's going to tell you these are the arguments. So the object to be converted, the format, a character string, and that's using this strip time. And you just scroll down, it tells you how to use a strip time function. But we want to know what the format arguments are. So we go down here and you can see %B is the abbreviated month name, or abbreviated month name. Capital B is the full month name. And so on. So M, little m, is the decimal number. So 2-digit number for month 1 through 12. Capital M is actually minutes. Sometimes there's time in there. But you would just sort through and find this. So lowercase y is the 2-digit year. We're using capital Y as the 2 or 4-digit year, and so on. But you don't need to worry about that because I gave you the correct code here. So we'll just run this. And there's no errors over here. And we'll look at the structure. And you can see event code is a factor, loc code is a factor, com ID is a factor, river is a factor, pool is a factor, date is a date, e-time is numeric, common and Latin name are both factors. So we look good. So this is the next step, and this is the most important thing to do. If you don't do your quality control, so QA/QC stands for quality assurance, quality control. If you don't do this right, none of your analyses are going to be right. So a very simple thing, and maybe the first step you should always take, is just to do a summary command and look at it. So this is going to give you kind of a summary of each variable. For some, it doesn't make a whole lot of sense if it's a factor variable, but it will tell you, say, the number of NAs in there. So we have several NAs. So if we look at E time, it gives us the minimum, maximum, third and first quartile, the mean and the median. That may be useful. I tend to look more at the maximum than anything else. But really what we're interested in right now is the NAs. So for temperature, you can see we have 204 NAs. And for, where is it, weight, we have 50 NAs. And I commented this out for you guys. And I guess just ignore length. So we're going to remove that. So we're going to look, I just want to show you this nrow command. So it's number rows of your Ohio data frame or object. If I hit that, you can see we have 65,192. I could have seen that from the structure as well, but this is a little cleaner. It just shows me that. So this is the same syntax as before. Take the Ohio data frame and pass it on with this piping command to the drop NA function. What this is going to do is going to drop all rows where there's an NA in your temperature and your weight column. And it's going to assign that to the Ohio data frame. So we're overwriting the Ohio data frame with our new cleaned data frame, partially cleaned. So if I run that, you can see we now have 64,988, which means we dropped 204 rows of data. We had 204 rows of NAs in temperature. So we are going to assume that those 50 NAs in weight were also NA in temperature. We can verify that by just rerunning summary. So weight, again, has no NAs. And if I find temperature, you can see there are no NAs. So that's good. We're ready to move on. The next thing here on line 74 is the erroneous values we're going to look for. So again, that summary command is useful. And I'm going to direct you to the temperature column or variable where we have our max is 46.28, which is equal to 150.3 degrees Fahrenheit. Another way, besides doing the summary, if you're not someone who likes to just look at a bunch of numbers, is to visualize it using a plot. So box plot is a really good way to do this. You just type box plot and then in parentheses, your data frame $ temperature. And the $, if I didn't mention before, is just the way that you can pull out variables within a data frame. So when you type in your object, so in this case OH, and put in a $, in RStudio, it pops up with this nice list and you can see all the variables. And you can select whichever you want, or you can type it out by hand. It doesn't matter. And then it'll show you, it'll just data dump everything in that column. And this is more of a vector format here. So another way, well, let's run that first. And hopefully, yeah, that pops up. So you can see we have one value that's pretty high and separate from the rest. So we can assume that's probably erroneous. Another way to do that is just with plot. Again, just same syntax, and run that. In this case, the x-axis is our row number, so it's the index. And then the y-axis is actually the temperature, so that's what we're interested in. And you can see that value is way up here and far away from everything else. So we're going to remove that. We're going to use the same syntax as before. We're going to take our Ohio data set and we're going to pass it on this time to a filter command. And we're going to use a logical operator inside that filter command. So it's going to return true or false. I have to do, hang on. So if I do Ohio $temp greater than 46.28, see, I get a bunch of falses and there's one, maybe if, I don't know how many trues, but there's a very small amount of trues in here. But you can see they're mostly false, and it's going to select the one that's true. Well, it's going to select, in this case, since we hit less than, it's going to select only those that are false. So, and these correspond to row numbers. So the way you can look at that is like this is row 1 from column temperature, 2, 3, 4, 5, 6, 7, 7, 8, and so on. So it's just going to remove the one that's true. And then it's going to, again, assign it back to Ohio. So we're overwriting that data frame again. And if we do our plot, you can see it's gone. So the next thing, we need to check typos, and we're going to do this within our factors. So we just hit structure Ohio. And we can see right off the bat, like, I don't care about event code and load code. We're not going to use those. COM-ID, we're not going to use. Latin long, we're not going to use. River, 1 level, that's fine. It doesn't matter to me as long as it's Ohio River, like, as long as it's 1 level, I know that it's fine. There's no typos in there. It's good. So pool, there's 22. So I want to check that and make sure those are all good. And then I have my common name, which is 125, and Latin name, which is 125. It looks good initially. They should be the same number. But I want to just make sure that everything in there is something I want to use. So I'm going to look at those. So the command I'm using here, and I've nested it, is unique. And this will pull out all unique values for, in this case, the common name. So I'm just doing Ohio $ common name. And it's not really organized. It might be useful to have it organized. So you can nest it if you want in sort within the sort command, like I have here, and now it's alphabetical. The other way you can do that is with piping, and just put sort here and just leave those empty. And that's exactly the same. I nested it just because that's kind of the default way to do that. So I went through this list. You would have to go through this list. I went through this list. I don't want these hybrids. I don't want anything that wasn't identified fully. Yeah, so like the Microptera species, I don't want. I just want the ones we know for sure what they are. So I spoke a little bit about vectors earlier. A vector as opposed to a data frame. A data frame has rows and columns. A vector is simply just a string. So you could have a numeric vector. The way you create that is just doing C parentheses, and then it might be 1, 2, 3. That's a numeric vector. Or you could have a character vector. Again, C, and then it'd have to be in quotations, A, quotations, B, quotations, C. It's just a string. You could have logical vectors, factor vectors. Well, I don't know if you have factor vectors. You have logical vectors. Usually they're just character and numeric. In this case, we're creating a character vector with the names of all those species we want to remove, which I listed here. And I'm going to name it rmcom species, so SP. So remove common species. So if I just run that, and you can see, let's look at the output, boom. So that's all there. Now I'm going to create a new object, which is the rows, for which I'm going to remove the common species names. And I'm going to assign it to that. So this which command, it will output row names for which a logical operator is true. So here I want to know which common names within the Ohio data frame are within, so percent in percent, the remove common species vector. And it doesn't matter that these are different lengths. It's just going to say which ones match. So if I run that, you can see I get a string of numbers or a vector of numbers. I look at that vector, so I can type in length and then put the vector object in there. It'll tell me there's 1,948 rows that I want to. And then these values correspond to the row numbers where this is true. So I'm just going to do this n row again. We have 64,000 and change. And then I'm using indexing here. So indexing for Ohio, you put in, you put in the object you're interested in and then use brackets to index. The first one is the row, second one is the column. So if I want to look at row 1, column 3, that's what I would type. And that's what it is. You can use vectors within that to get multiple rows and columns. You'll pull out first 3 rows, first 3 columns. But here, what I'm doing is I want all rows, or all columns rather, so I'm leaving the second part blank, and then I want to remove only those rows for which this is true. So I save that to this. And since I want to remove them, I'm going to put a minus sign in front of it. And again, I'm just using the Ohio data frame that we've been working with, and then I'm going to assign it to itself. So I'm going to overwrite it. So I'll run that code. And then you can see I now have 62,968 rows. If you did the math, that's how many I removed. So now we're going to look at the Latin names and do the same thing. There's a bunch of Latin names. This is what I pulled out. This one's okay because it's Saw Guy. I like that. This one's okay because it's Gravel Chub. I want to see that. So I'm just getting rid of this and this. So I made a new vector, character vector with just those two. And this time I named it RM lat name. I'm doing the same command, except for I'm doing Ohio Latin name in RM Latin name. And it's going to return the same vector. It's just going to be the rows for which that is true. And I'm going to run that same code, but with the remove Latin name rows now. You can see I removed, it would be 740 rows. Now we got to look at the pool. So I'm going to do sort unique Ohio pool. And you can see in here, now I pulled it out over here, Markland. And then there's a Markland that's all capital. There's a McAlpine with a lowercase a, McAlpine with a capital A. A Willow Island with a lowercase I, and a Willow Island with a capital I. And we want to fix all that. So we're going to take the Ohio data frame that we've been working with, pass it on to the mutate function. We're going to take the pool and we're going to change all the characters within that column, the pool column, to lowercase with that function. That'll also, by default, make it a character, whereas we want it to be a factor. So I'm going to nest another piping command within that and add factor afterwards. And because I'm piping, it'll just pass it through and I can just leave these blank. So if I run that and then look again, I'll rerun sort unique pool. You can see they're all lowercase and there's only 20 levels now. So I resolved that issue. And then I would save this. I want to save it to my clean data folder. So you use this write CSV function. The first argument is the object, in this case, our Ohio data frame that you want to save, comma, the file, and you need to write the path unless you want it to just save in your main directory. So data / clean data / and then the name of the file you want to save it as Ohio R fish clean, and you have to include the extension, so .csv. Now I have another comma, and I use this row names equal false, so that will just remove the row names. In this case, it's just 1, 2, 3, 4. In the empty cars, it was the name of the cars. I don't particularly want that. If you were doing empty cars, if you're going to save empty cars, it might be useful to not use this command or to just change this to true, because you might want to know what cars they are. But we didn't name our rows. I don't need extra column of just 1 through however many rows I have. So that's how to load and clean your data. We're going to move on to visualizing data. Again, if you had closed RStudio, you would have to reload these packages and your data. So this is all exactly the same as what you saw before. but this time I'm adding this piping command, and I am changing how it's reading in these functions all in one step. So now I can just put my cursor here on line 9, control enter, and it runs it. And if we look at structure, date's a day, and they all are correct, I promise. So we want to visualize our data next. This is a good step. And truthfully, I broke this up, but visualizing your data is part of quality control. But it's good to have it separate. And you generally have to do it at several points. So I broke it up just so you have a specific script for it. First, I want to look at the levels. So these are the levels of common names. These are all the unique. So when you have a factor variable, you don't have to use the unique command. You can do levels, and it'll output the unique levels. So these are just all the different common name, the different species we have. And they're sorted alphabetically because of this right here. But we're really only interested in largemouth, smallmouth, and spotted. I gotta check my email real quick. Okay, I'm back. So we're only interested in largemouth, smallmouth, and spotted bass. So I explained this aggregate command in the previous video, and that's what we're going to do. So we're going to, you can read this as count on. This tilde reads as on year. And if you were plotting, and it's kind of generally the same syntax for plotting and linear models, it would be y on x. Again, you have to separate by a comma, and then you have to tell it what data, and I want to take the Ohio data frame we've been working with. And in this case, I want to subset the rows where the common name is really equal. Equal is a logical command. So if I take this, highlight, and put it in my console, it's going to say true or false. It's going to select only those rows where it is true. So where it is largemouth bass, and I have a comma here, and I'm leaving it blank. So I want all columns. That's what it's telling it to do. You need a comma again to separate the commands. The function, fun capital, I'm going to be using is sum, because I just want the sum of the count for all largemouth bass by year. So that's the aggregate command, and I'm going to assign that to this new object called count LMB. So if I run that, you can see, and I ran this as well, you can see that it gives me a new data frame with 2 columns, year and count, and it gives me a count of largemouth bass for each year. The maximum is 273. If you didn't know that, or if this was like a really long, fed like 100 years or something crazy, you could do max and then just do count LMB, this object we created, $count. So what is the maximum count? Yes, 273. So that's going to be useful for setting our Y limits. So we're going to make a bar plot here. In this bar plot, I think I already showed you, this first command is the height of the bars, and we want that to be the count column. So just count LMB $count, comma, what are the names? So the name arg equal count LMB year. So it's going to name our bars. Axis name equal true. Y-lim, it starts at 3 as our lowest. I'm just going to go to 0, and then I want it to be a little larger, so I'm going to 285 instead of 273. LAS equal 2 simply rotates the x-axis label, so the years are going to be vertical instead of horizontal. That way they don't overlap. I want to name my Y lab, so Y lab. If I wanted to name my X lab, it would be X lab. Y lab equal count. And then I want to make a main title. So it's just main equal, in this case, largemouth bass. So if I run that, and you'll notice I'm assigning that to this LMB bar plot object. If I run that, it creates my bar plot for me, which came out exactly as I expected. And then I want to do a text. So I want to put the count for each year above the bars. So I need to use this LMB bar plot object that I created. And this is my X. So it's the position along the X axis. It's where each bar is. And the position doesn't correspond to 2000, 2001, 2002. It's coded differently behind the scenes. So that's why you need this bar plot object. The Y position is going to be the count. So just the height of the bars, and then +5 because I want it to be slightly above it. And then the labels, what I actually want it to put there, I want the counts again, but I'm not putting the +5. I just want the counts, the real counts. So I'm just subsetting out the counts column from that. So if I run that, you can see it put the counts there. And you can play around with adding +8 or 9 or 10 or whatever, just to make it look prettier if you want. So that's what we're going to do for questions 3A and B on your homework. You're just going to do it for smallmouth bass and spotted bass. I think I worked through this in class with you. This is all basically the same. You'll notice I changed the name here to count SMB. And I'm doing a little something different here. So this is a subset command. It's the same as the indexing version. It's the same output. However, it's a little easier to read. So I'm taking the Ohio data frame and using my piping command to pass it on to this subset. And within the subset, I'm using the same logical command. So common names, I don't need to have Ohio $ common name because it's passing it on with the piping command. Really equal smallmouth bass. So it's the same, it's just using the subset command. You can do it either way, whatever works best for you. It's the same formula and the same function. So if I run that and then double click here, you see that. So say, what I would recommend for the homework is just take this, Control-C, go down to here, Control-V, change this to SPB for spotted, and then change that. And then you can click here. So these hashtags are how you comment things out. You can see that I've used that throughout, so that R doesn't count it as code. If I were to just type words in here like note, you see R's trying to figure out like what it is, and it's like, hey, this is weird, I don't know what that is. It thinks it's code, but if you use the hashtag, it doesn't. So if I click here right behind the hashtag and do Control-Alt and then arrow key down, I can get multiple cursors and then just hit delete. And then you'll notice that these errors come up. Oops. So these errors say, hey, there's something going on here, and it has a little squiggly here, there's a little squiggly here. There's an X rather, not an arrow, an X, and there's squiggly here. So it's saying it's just missing arguments. Here it's saying it's missing an argument. Here it's missing. So what you need to do is take this and Control-C and click here. You can do Control-Alt and click again, and then Control-V. You might want to change the Y lim. So if I look over here, 900 is the highest, so I'll just do 925. Oops, and I missed one. You can see all of those are gone, and this pops up. Hey, it's like, why are you starting with an underscore? So I want SMB bar plot. So that's all good. Oh, and I need to change this to smallmouth. Make sure you do that. And then here it's still saying this is missing. That's where we're going to put our bar plot. Right? So now there's no errors. You can see if I just run it, I have my bar plot, and then I'll run this. I have that. Now it's not perfect. Maybe you want to play around with it a little bit, but to export this, simply go export, save image as. Right now it's not in my figures, it's in my main directory. You can double click figures and hit open, and then just give it a good name. Yeah, smallmouth bass count. And now it's saved. So if I open, go to figures, you can see that figure. And that way you can use it for the homework assignment. And you just do the same thing for the spotted bass. So now we're going to move on to data analysis. Again, I don't need to do this, but I'm going to. Everything looks good. Now we're going to create a new variable called catch per unit effort. So we're doing the Ohio $, and you'll notice the last variable here is weight. If I were to look through, there's no catch per unit effort. I'm creating a new catch per unit effort variable here. This is my assignment operator. And I'm doing that by just using Ohio $count. And I'm dividing count with this. This is how you divide by E time, so electrofishing time. So it's going to give me the amount of fish I caught per the time I spent trying to catch fish, and that's catch per unit effort. So if I just run that code, nothing shows up. If I look at structure, I have catch per unit effort now. And again, you could use head, catch per unit effort. So now we need to create a new data frame called catch per unit effort. So we're going to take our Ohio data frame, which has our new catch per unit effort. What we want is we want the average up. We want the average catch per unit effort, the upper and lower confidence intervals for all species and all years. So this is like aggregate, except for doing with aggregate, you can only specify, like you can pull out and do just for largemouth, just for smallmouth, or you can do all species, but now we can do individual species and every year. So that's what this group by command is, and we're using piping to pass it on to group by. So common name and year, and then pass that on to summarize. And then we're creating new variables here. So we're doing catch per unit effort average, and that's just mean CPUE. And it's gonna, you don't need to use anything fancy here because it's gonna apply this grouping that we put up here. And then for our upper confidence interval, we're using this quantile command. The first one is just what we want the quantile of, and that's our catch per unit effort. The second argument is which quantile. So we want the 95% quantile. That'll be our upper quantile. This just means remove NAs. Don't name anything. This is just the type it's using. Don't worry about that. The only difference here for lower confidence interval is I'm doing 0.05. Everything else is the same. And then I have this just so I can get the number of observations. This is like my sample size. And I'm also just passing that on to this arrange function, which is basically It's like sort in Excel. So I'm sorting by common name and then year. So for 2000, I'm going to have all of the species within year 2000 in alphabetical order. And then I'm going to go 2001 and have all the species in alphabetical order and so on. So that's what this is. So I'll just put my cursor up here on 29 and control enter, run it. It gives you this little thing, summarize as grouped, blah, blah, blah. It's just saying, hey, it grouped it by what I said to group it by. So if I look at this new data frame, and you can ignore all of this, this is just attributes that it saved it as. It's a grouped data frame now. And I only have my common name, my year, in those 4 variables I created. Common name is still a factor. So that's what I expect, because it's going to get rid of everything that's not used in this new data frame. And then I saved it again, just so I have it, and then reloaded it. So I'll reload it. And you can see it changes slightly because I didn't set all of whatever I did before as far as attributes go, but they don't matter. But it is still a grouped data frame. It still has all my variables. I guess common name's character now, but it's fine. It'll run. So I'm doing this just to help you guys. We're going to find the y-axis limits. So I'm going to use my cache unit effort data frame that we created above. And I'm going to create a new object called y-limbs. I'm going to pass the cache unit effort data frame on to this subset command. And this should look familiar. It's saying select those common names that are largemouth bass. So those rows where largemouth bass are present. This operator is another logical operator. It means or. You could use and. It wouldn't make sense in this case because we get 0 because there's no fish that are largemouth and smallmouth. We want largemouth or smallmouth or spotted. So that's why I have that. So we're only selecting these 3 species. And we're passing that on to this select command, which will only select common name, year, upper and lower confidence intervals. Honestly, I could just do upper and lower, it's fine. So I'll run that. And now I have this y-limbs tibble, which is same as a data frame, just shows this is character, this is integer, these are numeric. It has a different way of saying that. And it only shows you the first 10 rows instead of overwhelming your console. That's the gist of tibbles. You don't have to worry about them. They're fancy data sets. So I want to get the y min and the y max for my axes, my y-axis. So I'm going to use this min command. I'm going to use the y-limbs data set I just created. And I'm going to use for the min, a lower confidence interval, and for the max, the upper confidence interval. So I'm just going to run those. And you can see this is what I get. So this is just, again, how to subset out only largemouth bass, making sure that the subsetting command works. So we're going to plot here. We're going to plot the average catch per unit effort on year. So this is going to be our X. This is going to be our Y. We're going to tell it we want to use catch per unit effort data, but only the largemouth bass. That's the same you guys have seen. This type equal B means both lines and points. If I did type equal L, it would be a line. Type, I don't know if it's P, would be points. You wouldn't even need to include that if you just wanted points, because that's the default. LTY is the line type. 2 is a dashed line, 1 is solid. You can look that up online. PCH is the point type. 19 is a small black dot. There's others, you can get triangles, whatever. But that's what I have, and you don't need to change that. You can if you want. So xlim, you give it a vector of numbers. In this case, we want years, 2000 to 2020. Ylim, the vector is our y min and y max that we calculated above, and that will make it easier for you guys when you go to answer these questions. So this is the main title, Ohio River largemouth bass. Y label, so you'll have to change that to smallmouth and spotted. This you'll have to change to smallmouth and spotted. Everything else can stay the same. Y lab, catch per unit effort. If you wanted to do the X lab, it would be year. Maybe we should put that in there. XLAB equal YEAR, and then don't forget comma. And then BTY equal N just means no box around it. So if I plot that, you get a nice little plot, line plot, I guess, of your average catch per unit effort for largemouth every year. This polygon command is what we're going to use to set our 95% confidence intervals. So you're going to give it a vector for your X and a vector for your Y coordinates. So you need to do C parentheses. The X coordinates are going to be your year, because remember, we're doing catch per unit effort on year, where year is the X axis, but we only need largemouth bass. So the first one is just going to be catch per unit effort year for largemouth bass. And then you have to use this reverse to complete the polygon. You have to reverse it, and then it's going to be the same, just year. So this is just making it backwards. And then for the Y, it's the same. You're creating a vector, except it's catch per unit effort. It's the upper confidence intervals, and then only for largemouth bass. And then the reverse for the Y coordinates is the lower confidence intervals for largemouth bass. And it might get confusing with your parentheses, but you can see if you click, it'll highlight them. So this color, you don't need to adjust. Cull equal is just saying what color should the polygon be. I use this adjust color function. I chose gray 0 because it's kind of like a light gray separated with a comma. Alpha.f, this will set your transparency. I put it to 0.25. And then this last thing, border equal NA, so no border around the polygon. So if I run that, now you have a shaded region representing the 95% confidence intervals of your catch per unit effort. The next thing we need to do is we want to run a linear model. So we're interested in, is there a trend in catch per unit effort over that time period? So LM is the function we use for linear models in R, and it's the same syntax. So catch per unit effort on year. And then notice here in data, we're going back to our Ohio data frame. That's because we want the natural variability within the data. We don't want the aggregated data that is averages. So we're doing that. And then we have, again, this same subsetting command for largemouth bass. And then we're assigning that all to mod LMB. So if I run that, and I just grab this mod LMB, you can see this is the most basic way, this basic output. It shows you the formula. And then it shows you the intercept and the slope, which isn't very much of a slope. If you use this summary command and put the mod LMB object within it, you get a little more detailed output. You still have the formula. It gives you residuals. And then here under estimate, you have intercept, and then that's your slope, but it also gives you standard error for each, the t value in the p, so you can see neither the intercept or slope are significant. In this case, the intercept is not significantly different from the average for the whole time period, and the slope is not significantly different from 0. The r squared I'd like is the adjusted r squared, and then it has the f statistics. This is your f value, the 1.211. And then these are your degrees of freedom for your f test, 1 and 1,109. And then this is your p value for your f test. So you can see it's not significant. There's no significant relationship between catch per unit effort in year. And normally we wouldn't plot that because it's not significant, but I'd like you to plot it. So AB line is how we're going to do that. You could do AB, it's just going to make a straight line. So it's like slope intercept. But it's really, it works nice with these linear models. It's just going to pull the slope and intercept out. So you can just fill it in with the linear model object and hit Control Enter, and it puts that line on your plot. You can see it is basically flat. The next thing we're going to do is create a legend, and we're going to put the statistics for our model in that legend. So you do that with this legend command. The first argument is the position. I'm going to put it in the top left. It could be top right, bottom left, bottom right. There's probably others, I think center or top center. I'm not sure. You could look it up. You can also use XY coordinates. This is the easiest. Second argument is the legend. So what's going to be within the legend? That's going to be a vector, and it can be mixed in this case. So this expression command here is going to allow us to put in a nice mathematical formula. So this r up caret 2 is going to do r superscript 2. Equal is going to be interpreted as just equal. And then I rounded my r squared, which I got here from my adjusted r squared from the summary. The next one I want is the f statistic. So I'm going to do expression f and then use brackets for subscripts, and then list in order to get two values, because we have 2 degrees of freedom. Again, you get your degrees of freedom from right here, and then the equal your f statistic, which is right here. And then you can just type in p equals 0.27, which I got here and rounded. And then this bty equal n just means don't put a box around my legend. So I'm going to run that, and you can see it put it here, and it looks kind of nice. So you're going to, again, do all of that for smallmouth bass, and you're going to do it again for spotted bass. So I'll just work through this first one, and I would recommend the easiest thing would be just Control C, Control V, scroll back up, click here, Control Alt, down, 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 down arrow, delete. And then I need smallmouth. I can just highlight, Control C, then click, Control Alt, click, 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 and Control V. And then the main needs to be, what was it? Ohio River. It's going to be smallmouth though. Oof. This stays the same, same, all the same. Yeah, all the same. All of it's the same. You just need to change these. This you need to finish. So SMB and then Control C. Yeah, finish these. So we can run this now. Now we have our plot for the Ohio River smallmouth bass and our shaded region. We want to run our linear model. Already fixed that, so we can just run that model. Already copied and pasted the model object, so we can look at that. In this case, again, not significant. Here's our intercept. Here's our slope. Here's our adjusted R squared, our F statistic, our degrees of freedom, and our p-value. You can see it's again not significant. We're just going to run that AD line though anyway and put it in. And then we're going to do the legend, which we have to fill out. The R squared is 0.0005. The degrees of freedom are 1 on 2666. And the F value is 2422. The P value is this, and you could round. So if I do that, and then boom, you're done with that. So just do the same thing, but change all those to spotted bass. And you're done with that homework assignment. Part of the homework assignment. The next, I wanted to show this. I didn't get to it in the first class. I know some had to leave in the second class. But I'm going to show you species richness. So we're going to start with our Ohio data frame, but we're going to create a new data frame for just, ignore this note, that's old, for just 2001. So we're going to pass our Ohio data frame on to filter, and we're going to select only the year 2001. Just sack, my dog wants food. So we're selecting only those years for 2001, and then we're passing that on again to another filter command. And this time we're selecting those pools that are not. So exclamation equal is not Montgomery, and the pools that are not open water. And then we're passing that on to our group command, our group by command. We want to group by pool and common name. So we want to know individual fish within each pool. And then we're going to pass that on to our summarize command. We're going to summarize the count. So we're going to get a sum count for each species within each pool. And we're going to get the average catch per unit effort for each species within each pool. And we're going to get the number of sampling events for each pool. And then we're going to pass that on again to the mutate command. And we're going to create a new variable called presence absence, or PA. We're going to put equal because that's how you have to do it. And then this if else command, it's a logical command. So it's if count is greater than 0. So if there's a fish there, put a 1 in this new variable in the row in that cell for this new variable. Otherwise, put a 0. So is it present? 1. Otherwise, no. And it's just greater than 0. It's present. Then we're going to pass that on to the select command, which selects only the variables we're interested in. And it's also useful to organize it because whatever order you put these in is going to be the order that it displays it in, like left to right. So we want pool, common name, presence, absence, and catch per unit effort average. And then I'm going to pass that on to this drop levels command, which is going to drop unused levels. And then I'm going to make it a data frame, so it's not a tibble, because I like working with those better. So I'm just going to put my cursor back up here on 155 and control enter and run it. Again, it tells me that it did what I wanted. So if I do structure and look at that, you can see it's a data frame, not a tibble. 567 observations of 4 variables, which are pool, factors, common name, factors, presence absence is numeric, and the average catch per unit effort is numeric. So let's just look, I guess, at the levels of the pools. That's right. So we had 20 pools, we removed 2 pools. Now we have 18 pools. This is a good way to check. So which which cells within the new data frame, the Ohio 2001 data frame, within the presence absence column are 0. And we want zeros. And we have currently integer 0, no zeros. If we look at the data frame, you can see there's no zeros. So we must have fish. We have more fish. Like not every species is in every pool. Like here you can see for Bellevue, there's only 20 observations, whereas we have what? Yeah, we have 70 species. So there should be zeros. We're missing 50 species from the Bellevue pool that all need to be zeros. And this is going to be important for calculating species richness. And so we need to use this add zeros command, which is from the FSA package. We're going to create a new data frame called zero catch. So the first argument is the data frame that we need to alter, or add our zeros to rather, and that's the Ohio 2001 data frame that we've been working with. The event var is like the pool. So it's like the event, where what's like, it could be a sampling event. In this case, we're using pool. So we want for each pool, we want to fill in the species variables that are missing. The species variable is our common name. So we're going to add common species. We're going to add this common name that's missing from Bellevue and all the other pools. And then the zero variable. So it's where is it going to add the zeros? It's going to add it to our presence absence column, and it's going to add it to our catch per unit effort average column because we didn't catch any. So we want those to be 0. And then, of course, I'm just piping this again and arranging it. So this is that sort command. It's another version of it by common name. This will sort. So as opposed to sort, which will only sort by like one variable, this will sort by multiple variables. So I'm sorting by common name, pool, and then presence absence. So we'll run that. And let me get a little more space. I'll run head, tail, zero catch. And you can see Bellevue, banded darter is 0. Cannleton, banded darter is 0. But there is some banded darter here and here and here. So that seemed to have worked, but we want to check more thoroughly to make sure. And this xtabs command is a really good way to do that. It's kind of a little more advanced way of making a table. The syntax is weird. It's just tilde pool and then data zero catch. And these should all be the same. So what we're looking for is we're looking for the same number, whatever number of species we have. In this case, we have 70 species for each pool. we want 70 for each pool, which would mean we have, it doesn't matter if it's a 0 or a 1, there's 70 observations within each pool. And we can see what the output is. It gives us our pool name and then the number of observations, and they're all equal, they're all the same, they're all 70. And if I wanted to go even further, I could do pool plus common name and then data 0 catch. This is going to look messy, but these should all be 1. So you wouldn't want anything greater than that. So you can see I now have, it obviously broke the table in half, or not in half, but multiple sections because it's very wide. But I have 1s now. So there is an observation for each species within each pool. It's probably a little further than we need to go, but that's very useful for things like this. So in order to calculate species richness, we need to go from long to wide format. And right now we have it in long format. And what that means is each row is an observation of, like, say, pool species and whether it's present or absent. But wide format, each row, instead of being a single observation, would be a pool. So we're going to have fewer pools. We're going to have 18 pools, so 18 rows. And then each column is going to be a common name. So we're going to have 70 columns, well, plus 1 per pool. So 71 columns. And then it's going to, we're wanting to fill that in with our presence absence variable. So to do that, we're going to create a new data frame called species. We're going to use our 0 catch that we've been working with. We're going to pass it on to this mutate command. And we're just going to change common name to character, which I think already happened, but it's there. We're going to group by pool. Then we're going to use this pivot wider function. The ID columns, so this is what's going to be created. This is basically going to determine the number of rows we have. I want that to be the pools because I want to know how many species are in each pool. And then the names from, so it's going to create columns from the common names column. So there's going to be a new column for each species. Then the values from, what is it going to fill in each cell? So we're going to have 6 rows and 70 columns. What's it going to put under each column? It's going to be the presence absence variable corresponding to the pool and species. Names sort equal true simply just organizes our columns in alphabetical order, with the exclusion of pool, which is going to be first. And then fill values equals 0. If it's not there, it'll just put a 0 in. And then again, I use add data frame just because I like working with data frames rather than tables. So I run that, and then I'll make this super wide, but we have 70, so it's going to look a little messy. You can see what we have here. The first column is pool. And then we have a new column for each species. And these are 0. If it was present, it's 1, 1, 1. And we don't necessarily know. We just know that the species was present. So there could be 100 banded darters and dash field pools. This is just saying it's present. And that's what you want because we're interested in species richness, which is simply the number of species present, right? It doesn't have to do with, abundance necessarily. So the next thing we're going to do is, well, this just helps to make sure everything's right. So this dim command, this stands for dimensions. So if I type that in, I get 18 and 71. So we have 18 rows, and that corresponds to 18 pools, and then 71 columns, which is 70 species plus the extra column for pools. And then I want to add a column for species richness. So again, I'm just doing species $richness. I'm using my assignment operator, and I'm using this row sums function. And this is a capital S. And then I'm doing species, but I'm only selecting the columns, and this is a typo. So I'm doing all rows. So I'm leaving that blank, and I'm making a vector, and I want column 2 because I don't want the pools through 71. So I only want the species columns. So if I do highlight that, control enter, you see yellow perch is the last one. If I scroll all the way up, a lot of scrolling. Banded darter is the first one, which is right. So you can see that. So I'm going to calculate the sum for each row for only my species column. If I didn't do that, it wouldn't work because you can't have a character value like the pool name. Like you can't get a sum from that, right? So that wouldn't work if I didn't have this indexing command. So I'm just going to do that. And then we'll look at it, and you can see it added the richness. So there's 20 species there, 40 there. Yeah. And I'm going to save that as species. I'm not really because it's already there, but you can. Then I'll look at this just to know how many pools we have. And I think, yeah. Yeah, so this is how many pools we have. So we're going to plot species richness for each pool. So this par, I guess I figured that out and just set the Y max for you guys. So I guess run that. This par mar, so this means margin equals C. It's just saying how much space to leave. And like you can think about it as like lines on a paper, like how many spaces, how many lines to leave in each margin. And it has 4 margins. So this is for our plot. So you have the lower, left, top, and right. So the first argument is the low one, the bottom one. Second is the left. Third is the top. And then fourth is the right. So I just set that for you guys. Just to make it a little nicer. Again, I'm making a bar plot object. In my bar plot, the height is the richness. Names are going to be pool. This is all the same except for this is species richness now. And I'm putting them vertically so you can read them. The text, the location is bar plot. The Y location is richness +1. And the labels are richness. So we'll just run that. And you can see, so for each pool, I now have a bar plot of the richness within that pool. The last thing we're going to do today is calculate the Shannon-Weiner species diversity index. So again, we'll just look at the dimensions. Now it's 18 and 72 because we added that richness. We want to look at this, but we don't want the richness column. So we're just going to do -72. When it's just one column, you don't need to use a vector. You can just do -72, and you can see the richness is not shown. So again, we're going to create a new variable. We're just going to do species $Shannon. And then our assignment operator, this diversity function comes from the vegan package that you downloaded. And this is going to make our life a lot easier. The first argument is the data. So we need our species data frame, which is this. And we can't use the first column because that's our pool. That's a character value for our pool name. And we can't use this 72nd one because that's our richness. We don't want to count that in our diversity. So we're removing the first and 72nd column, and we're using all rows. And you do comma index equals Shannon. There's other indexes that this function can do, but we're doing the Shannon diversity index. So you just run that. And then I want to look at species, but I only want to look at columns 1, so the pool, 72, the richness, and 73, the new Shannon diversity index. And you can see that here. So all those ones and zeros are still in this species data frame, but I only looked at those columns. So this is the last question. So 7, we're going to make bar plots of catch per unit effort for species, which I spelled wrong, for the Bellevue, Hannibal, Mendel, and Olmsted pools. I did it for Bellevue and Hannibal. You just have to do the Mendel and Olmsted. So again, I'm just using the same PAR-MAR as before. I'm not asking you to label them, the bar plots. So here the first, this is still the same thing. It's the height of the bars. I'm doing the zero catch per unit effort average. So I'm pulling the column out here. And then I'm indexing just for the Bellevue pool. And you notice I don't have a column, or a comma rather. That's because I already pulled out the column here. So it's basically a vector. And within a vector, you don't have rows and columns. So you don't need a comma. You just need those rows where the pool is Bellevue. So name arguments is the same. It's your common name. And again, you have to index the Bellevue pool. This is all the same, except for main has to be Bellevue and LAS equal 2. So if I run that, get a nice bar plot. This is my catch per unit effort for each species within the Bellevue pool. And then I can do the same for Hannibal, which I already wrote for you. And you can see it's slightly different. Then if you were going to do this for Mendel, so just Control C, Control V, Control C, or Control V rather, you can just literally Control C, copy that, double click, it makes a nice little box around all of these, Control Alt, double click, Control V, Control C, double click, Control V, and then you're done. Boom, 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 boom. Save it. Export it, and then answer the questions. Yeah, so that's it. That's the whole thing. I'll be sending out an email about the homework. Please, if you have any questions, meet with me, especially if you care about learning R. I know this was a lot to throw at you guys. I didn't realize how long it might take, but I think it's useful information, and I think there's enough here that you guys can reference this in the future when you have questions. So yeah, I'll upload this tonight. Hopefully it'll be uploaded by tomorrow. And if you have any questions, let me know, and I'll send out an email about the homework.